Morning. My name is Tim Young. I work at the University of Tennessee. I'm a professor there and recently joined the Bredesen Center as a data scientist in a joint appointment. It's an honor for me this morning to speak to you all at the 6th International Conference on South Asian Economic Development, an online conference. Actually, my first conference in my career speaking to a conference in India. So I'm very honored to be with you this morning, and thank you very much for the invitation. Theme of my talk, the setting we live in today. Machine learning and AI, they're evolving very rapidly in our world as predictive solutions for many applications: finance, economics, social media, robotics, manufacturing, etc. And really this kind of evolved, part of the natural evolution, I believe, after big data platforms were established. And we cannot argue, most of the students out there know the impact of social media, how that has transformed our lives and how we make decisions and interact with one another. But the underlying fundamentals that I'm going to talk more about today are really the statistical mathematical models and learning algorithms that support big data solutions. And in today's world, people want faster transmission of solutions to the end users, and some of these algorithms are very good at doing that. Big data are inherently messy, and they're generally unstructured and non-relational. So that's a big hurdle one must get over. And big data are inherently non-homogeneous, and that's where random forests and some of the tree-based methods I'm going to talk about today can be very, very helpful. They provide analytical solutions. That's really the theme to a very rapidly changing world, and the algorithms are rapidly changing themselves as we progress. So a little introduction here, but I can't go past Stephen Hawking here in his quote on AI. This is a very positive quote that he made. It's negative quotes about AI, but he said it would be the biggest event in the history of our civilization. And H.G. Wells also made a quote I came across where he said, "Statistical thinking and analytical knowledge will be important to future citizens as the fundamentals of reading and writing." So our world is definitely changing and changing very rapidly. In this world here of the AI, this was a slide that I was given by the director at the Stanford Disruptive Innovation Center, or Center for Disruptive Innovation. And the bottom line is we believe that machine learning and AI are evolving, learning quicker than humans. And on the right here, the robotics slide, robotics are pretty much very common now, and they're essentially outperforming human work. This publication he also gave me, or this, this slide, but he also, he looked at publications. And the predominant publications from the term 2010 to 2016 were in the computer vision and pattern recognition area. And a lot going on there with facial recognitions, optics, closed circuit TVs, being able to recognize patterns. And the algorithms I'm going to talk about today are very helpful in coming up with solutions there. My specific area in random forests and decision trees is more or less, we're not publishing quite as much here on the lower part of the realm here, but we're still publishing on the rise. So this slide, this is very my part of the world centric, United States. Predictive analytics are the keys to success and survival in the era of data science. No one can argue Jeff Bezos, Amazon, data is the new gold. He harvests data. They use AI. They use machine learning. They use big data on a daily basis to harvest knowledge to expand their business. Tesla, Elon Musk, self-driving cars. You definitely need very fast acting algorithms there. His SpaceX work. In your part of the world, I came across Tata Consulting Services, a very important AI data mining company. And then in our part of the world, FedEx. FedEx was one of the leaders in the logistics business, and they use data and tracking and labeling. They established essentially the benchmark for others to follow. And it wouldn't be do justice if I didn't have Steve Jobs up here, the great innovator from Apple, as far as data science and business success. So Industry 4.0, you'll see it spelled IE 4.0. That's the European spelling of that because it came from that part of the world. I think data mining, AI, and some of the work I'm going to talk about today can really help make the bioeconomy become the circular bioeconomy, become the reality. These algorithms and methodologies can identify sources of variation and interactions among variables, independent variables, faster and at a rate that humans are not capable of understanding or even have the knowledge to understand from the data. So I do believe with reducing or identifying variation, you can reduce variation, and by reducing variation, essentially you drive down costs and make this circular bioeconomy more affordable. If you haven't seen the movie Moneyball, it's for American baseball, and it's an older movie, and it was developed, it was a Moneyball, it was a true story about American baseball, about the art of winning the unfair game, and they used statistics and probability decades ago in American baseball to come up with a winning solution to compete with what we call big money market teams. And the bottom line is the students should definitely watch this if you haven't seen this. Cricket in your part of the world, I would assume the same probabilities and statistical analyses hold there. And I would assume the sports teams are probably using those to get competitive advantage from the data. In my world, I work a lot with manufacturers and machinery, et cetera. Are machines better than people, the human error factor? And right now, machines and robots are outperforming humans in making less mistakes in a lot of the studies that are done. So part 2, data quality. Models are only as good as the quality of the data. This is one of my former professors, quite famous in the United Kingdom and America, George Box, a famous statistician, one of my first professors at the University of Wisconsin. Great teacher, but he essentially said, yeah, all models are wrong, some are useful. And you've probably seen this quote. So just always keep in mind in a modeling effort, but it's also always only as good as the data. A couple splash screens here on my presentation. To the left, just a little illustration, but this is the data that Dr. Saha and I are working on. Very non-normal, very skewed data that we're working on. And these are some clusters from different data cells. And machine algorithms or machine learning and random forests, they tend to work very, very well with this type of data. And this was a slide from a former graduate student of mine, David Yurga. And essentially this bottom box chart here in the blue, that's root mean square prediction. Smaller is better. So you can see when he cleaned the data and processed the data, he got much smaller root mean square prediction, which is good. Versus unclean data. So before I get into the methods and the algorithms I talked about, predictive analytics is really not possible without data fusion. I do believe it's a big barrier to a lot of us, both in research and in business and economics. How are we going to process the data in a useful form? Now, companies like Amazon, Tesla, FedEx, they have whole groups and teams of individuals that run algorithms to do this because they know big data is inherently messy and they have to improve the quality of the data before they can process it for their learning algorithms. This was a slide taken from David Yurga's master's thesis where he essentially showed that processing data through not only eliminating outliers and other problems with the data set, but also using imputation, okay, can greatly improve predictive performance. And he developed an algorithm to fuse data real time using Microsoft SQL. He looked at data imputation algorithms for different methods, indicator, mean, median, random, last observation carried forward, the MIMC algorithm. And the bottom line here is he found better performance and predictability using imputation than not using imputation. But that's a talk in itself. And today we're going to talk about random forests. Tree-based methods. So an introduction, a little quote here again by Albert Einstein, and we do have to change in today's world if we're going to survive. So definitions, a lot of the work I work in is called narrow AI, where we're looking at historical data to make predictions, random forests, and deep learning. It's also supervised very much. There's a little bit of unsupervised work, okay? We're essentially looking at the outputs and we're learning from the functions and providing feedback to the algorithm. And then unsupervised really tries to find clusters we haven't discovered in the data set. I don't do a lot of work in that area, but that's a big area. And then this whole area of reinforcement gets back to this general AI area, self-learning, where algorithms are rewarded based on accurate estimates or accurate predictions and based on speed or efficiency of those predictions. Nice article there by Taylor in 2019 on that. So before I get into random forest and decision trees, I do have to mention deep learning because I talked about it in my earlier slides. And there's really these 10 areas of deep learning neural networks. And they're just different algorithms within this whole body of deep learning or neural networks. And the big one for like facial recognition and optics is convolutional neural networks, very popular. And then there's a long list, which this talk is not about deep learning, but I wouldn't do it justice if I didn't mention it. The neural network essentially tries to mimic the human nervous system, neural coding, and it provides a feedback loop. So it's essentially trying to have these inputs, right? And it's trying to get closer to the target, and it does that in a loop or iteratively. It processes through layers, and this is just one layer example, but these are multiple layers here of neurons. And these neurons essentially have functional forms that are both nonlinear and linear in nature, and they're making predictions based on the input layers. Okay? So the idea is they're very, very good. They are greedy algorithms. They tend to overfit the data, so they do have to be supervised to some extent. Liu here in publication 2018, I thought did a very good job in trying to organize the taxonomy of machine learning algorithms. And as I circled here in this slide, I'm going to talk about decision tree learning and Bayes classifiers, kind of random forest. I like this slide, but at the same time, it's a little bit over categorizing things because the current world, all of these algorithms are operating as an ensemble or a suite to make predictions. So where were we before decision trees, regression trees, tree-based methods like random forests? Well, we tried to fit a functional form, one functional form to data that could be clustered, okay, or have subspaces. And you can see here from the actual data points in the circles versus the fitted line or the functional form. This is a smoothing spline, which is a cubic polynomial that essentially fits data every 3 to 5 points, a cubic polynomial to that data, depending on your preference. And you can see the residual is just going to be larger with one functional form. This is another method, lowest, that was a little bit more linear, okay? But this residuals, this errors are still going to be larger. And regression trees came along and said, you know, back to my earlier theme, big data is inherently messy. Big data is inherently have clusters, okay? And this is just a simple linear fit as an example to a data space. And you can see the size of the error or residuals from the fitted line to the actual data. What regression trees do essentially is fit models to this subspace. And this model right here is a very simple one, as illustrated in the red lines, which would be the average or the mean. That could be the median. It could actually be a linear fit. I could fit a simple linear regression or multiple linear regression to that subspace. This would be somewhat of a linear positive slope, and this would be a negative slope. And in the end, when I sum up here, the errors for those subspaces relative to the fitted model, my overall generalized error is going to be small, okay? So that's the theory of regression trees in a real general sense, a real general idea. So there's two types of decision trees, both the categorical data called a classification tree. I don't work a whole lot in there, but it's very good at classifying categorical data, and then numerical data, which is a regression tree. And you can see in a regression tree, we're fitting functions to these subspaces as we go through the data. The general steps are the same fundamentally. You partition the data, you fit a model to each data partition, you stop when the residuals of the model are near zero or a small fraction are left. They tend to be greedy, they tend to overfit the data, so you have to have a pruning algorithm, okay, to essentially prune the tree so it does not overfit, and you improve your prediction in validation. This was just a slide from one of my earlier works back in 2012, We're using quantile regression, so we don't fit to the average like linear regression. We fit to either the median or some quantile, percentile in the data space. And the bottom line is, I tried to point out here, it's a manufacturing example, but we could identify interactions that the human can't identify. This hierarchy of interactions, and we lead to an optimization. And this IB is like a internal bond or tensile strength. So you're trying to maximize that. So we can find an optimal solution very, very quickly. And it's used a lot in robotics now, because robots have to make this not only one decision, they have to make, like a human mind, a hierarchy of decisions to come up with a solution to the problem. And this is where we're really going, that these can identify quicker than humans, these interactions that the human cannot see in the data. So brief history of tree-based methods. The first generation goes all the way back to 1963, first publication, and it moved forward. And we get up to the fourth generation here. CART, which was an early generation, has evolved here, and it's still around. It's in a lot of commercial software. You're probably aware of CART out there. So it's very popular. But then back in the late 1990s, this Bayesian idea was presented by Chipman. And I'll talk a little bit about that later on. But I like Guide here by Dr. Lowe at University of Wisconsin. It is free. You can download it from their website, University of Wisconsin. And BART is the algorithm I'll talk quite a bit about at the end that Chipman also published later in 2010. So a lot going on here. So this is classification. We're trying to classify things, and we're trying to find a random classifier. And we're using a number of methods to do that. So let me give this example I tried to put together. We have blue zeros, okay, and we have red ones and zeros, as I indicated here. And logistic regression does very, very good here at organizing it into two groups. But where regression trees and decision trees go is they take this subgroup and they split it again, and they split it again, depending on how much data you have and how many subspaces you have. So this goes far beyond logistic regression. And now we get into the idea of boosting coming up here, okay? So boosting generally has better predictions. The decision trees you saw a few slides ago had very good explanatory. I could look at those interactions, I could quickly find the optimal space, the optimization, and I can make a decision. However, they suffer a little bit from poor predictability, as I illustrated here on the slide, or the figure on the left, okay, because the way they essentially fit the model to the subspace. They have one global model, okay, and they fit it to the subspace. And you can see the R-squared invalidation is 0.720. You can see here the R-squared invalidation for these boosted trees, okay, is much better. The R-squared improvement is up to 0.867 in validation. So what's going on here? Well, boosting is a gradient descent method. So we have some form, and boosting is a form of bootstrapping or resampling of the data that I illustrated, that I'm going to illustrate here in a minute. And essentially what's going on is we have this loss function, which has something to do with the error, generally the squared error, and we're trying to minimize that, okay? And the red line here is the validation or testing data, and the blue line is the training data. So as we go through here, we reach a point where we cannot improve anymore, okay? And boosting gives us a better predictability, but it's we're essentially using this gradient descent method to decide when to stop the boosting. So this fourth generation random forests in Bayesian additive regression trees, or BART, okay, they're really the idea, the wisdom of crowds, okay, that a bunch of weak learners, okay, is better than one global learner, okay? And I tried to illustrate that with this figure here from this article, where you have these little yellow, okay, kind of circles, and those are the weak learners. And we're going to put together a bunch of weak learners. In this illustration, it's only 2, okay? But you could have more than 2. You could have 3, 4, 5, 6, 7. You get into computational issues, the more of those you have, okay? And you can keep going as many nodes as you'd like to have, okay? But the idea here is that when I put these weak learners together, so using R squared, for example, the coefficient of determination, okay, that many of you are familiar with, okay. The R squared for the global learner, let's say, is 0.82, okay, in validation. But the R squared for the weak learners is only like, say, 0.70 in validation. But I have a number of these 0.70s in the data space. And when I look at the sum of the R squareds, you cannot sum the R squareds, okay? But when I look at the sum of the squared errors and make an R squared a coefficient of determination, instead of having a global learner with an R squared of 0.85 or 0.82, now I have a group of weak learners that have an R squared in prediction of 0.9 or greater. And that's the idea here with boosting, and that's what's going on in random forests. So I tried to illustrate that again here. And so really what's going on is we're resampling these, this data space. In this example, 1, 2, 3, 4, 5, 6, same size N here. And then I only sample, I only take the one, I take a 1, I take 2 2s, a 3 and 2 6s, and what's my prediction? Then I go back and I resample again, and that next sample may be what? It may be a 4, a 5, and a 6, and the rest 6s, 3 6s, same N, and then I get another prediction. And I keep doing that here up in this example, up to 600 of these weak learners, okay? Then I average all the predictions, and I get a random forest prediction. And that just generally outperforms regression trees by themselves. And they're really looked at as a part of machine learning and AI as a very important solution for those areas of research. So let me talk briefly about Bayesian additive regression trees, or BART, okay? So in BART here, we have a prior model, which is generally uniform or normal distribution, okay? And we develop a posterior distribution from the data, okay? So the red line is our initial model, okay? And then the yellow is our final distribution. And it doesn't have to be symmetric. This is just illustration. It could be any non-symmetric distribution that's better performed. And the blue is actual, okay? That's the real world. And the prediction error is smaller between the yellow and the blue, obviously, than the blue and the red. So the idea here is that a frequentist, okay, not using Bayesian inference in the regression trees, is assuming some prior model, such as the Gaussian or the normal distribution, and then we're collecting data. We estimate the mean and the variance, or standard deviation, sigma, and then we make a prediction. So we're kind of here, okay, versus the posterior prediction, which generally tends to outperform. And just think about the average of a normal distribution and then an average of a posterior that's skewed. Well, that average is going to move and tends to be more accurate, okay, than the average of maybe a normal or predefined model. So let's talk about the results then. Let's get to the real key part of the discussion here, or the lecture today. And I like this quote from John Tukey. A lot of you know Tukey-Kramer's test in statistics. So an approximate answer to the right problem is worth a good deal more than an exact answer to an approximate problem. So economic applications of random forests. Wow, are they out there? There's a plethora of literature in this area. This is some examples here, and this is in the Euro area, GDP forecasting, which is very important, okay? 2010, kind of interesting. We could not have predicted the COVID crisis, so I'm not sure how those forecasts worked out for them. But essentially what they're doing here is, back to my earlier theme, it's a combination of algorithms. So when they combined RF here, or random forests, with their linear traditional models, you can see here that they got much better to the economic outlook, okay, with the triangles here, the triangle line, okay? And so they would be what? Maybe better predictors of the forecast, okay? So again, traditional methods, look at how close we get with these newer methods for forecasting GDP. Here's one, central bank independence, okay, the CBI, okay? And it comes from a large database of the OECD, which are pretty much Western countries. And it's really determined based on the importance in respect to the CBI, which is a key determinant in economic forecasting. And the bottom line here is essentially when they ran these trees, random forests, over and over, okay, they essentially came up with a key recurring theme, which is this EMU, independence variable, which mainly reflects a change in the institutional design of the monetary policy. That was 41% of the total variation in CBI. So if I can estimate that using random forest methods, and many economists in the audience use econometric and time-based methods, which are very good, this gives me a little bit better determinant, okay, for forecasting economic behaviors and financial behaviors. Here's one that a lot of the students like. This is forecasting markets, financial markets. And they compared an autoregressive model with that of a machine learning model and to actual. And it was very interesting here because obviously if you can forecast markets, you can make money. And you can see as they move through, it's not a great, I took it out of the publication, so it's a little hard to reproduce here by Long and 2008. But you can see as you move through the data that their forecast got worse over time. The dashed line here, 22 days. But their forecasts were pretty good here at the 5-day. So if I can forecast 5-day activities of financial markets, that might give me some early warning signs or early opportunities here in the financial markets to make money. Obviously, the 1-day forecast is very good. That would be day trading. And there's a lot of news in the New York Stock Exchange in America on day trading and GameStop stock. So economic applications of BART. Another one here, this goes back to financial engineering, stock indices, which is very, very important, forecasting the stock indice. And goes out quite a ways, and essentially they ran BART and comparing that to time series predictions. A little hard to see, apologize for that, an illustration came out of the article, but essentially that's the confidence bands, the observed is in the blue, and the other color is the predictions. But the bottom line is over here to the left in the blue. The mean difference using a time series technique had a difference from the mean, actual from the prediction model of 56.1 points, okay, and a standard deviation of 1,030. The BART prediction had only a mean difference, okay, a delta of 0.284 and a standard deviation of 242. So tremendous improvement here in the Bayesian predictive capability. This is another economic application of Bayesian influence and BART models where they essentially outperformed German economic forecasts, okay, of growth compared to traditional methods. I don't have a lot of time to go through this, but essentially over here, they were showing the R-squared improvement, or the R-squareds, which were improvements over other R-squared methods. Now, let me get to the work I'm working on with Dr. Saha at South Asian University. Gosh, we met at a conference at the Atner in Athens, Greece. The Atner is a Athens Institute for Education and Research. I'm on a number of committees there in both the data science area and statistics. And we were in the same concurrent session that day. And she talked a lot about her work. And I met her. And then she, I guess, heard my talk on machine learning and random forests. And we said, why don't we collaborate together? And I've never had an opportunity before to work with another researcher directly, collaborator with India. And so it was kind of neat to start this collaborative effort. And so we're, in this one example, this preliminary results, we're actually modeling the data right now. We hope to publish in a high impact factor journal. But the theme was going to be definitely BART. If I have anything to say about the publication, because what it's doing is essentially, we're trying, in this case, trying to use real sales, the variable, to predict net fixed assets as a measure of size. And the bottom line, look at the BART R-squareds in validation over 10 validation runs. It's the winner here, 6 of the times versus boosted trees and bootstrap forests. So BART, again, tends to, of all the random forest methods, it tends to be a very good indicator. And what's more important here, illustrate here quality of predictions, just as XY scatter plots, and you can see that BART is a better predictor, okay, than the boosted or bootstrap forest. But what I was trying to say here was essentially we're regressing or we're developing those random forest models for real sales, essentially on these 6 independent variables here. And you can see the recurring theme that occurs in these variables over time. And so essentially, they're really the drivers of this indicator, real sales. And this is very, very important. And these are recurring in the validation runs. This is 3, 5, and 1. And the bottom line is then we look at this as a Pareto chart, a histogram over all the runs. Okay. So another application I have here in manufacturing, predicting strength of materials. Again, we compared not only random forest methods, BART, bootstrapping, and bootstrap forest. We also compared that with decision trees, neural networks, partial least squares, and multiple linear regression. By far, BART had the smallest normalized standard error prediction as a percent. Smaller is better here relative to the boosted trees. Came in winner a couple times, but BART again is really, and this, we were doing these predictions in real time, because in manufacturing, if I can predict real-time outcomes, I can reduce variability, improve efficiency, reduce waste, reduce scrap. I can make more money. So conclusions. Random forests are becoming important, I think, in machine learning. They're underlying it in machine learning. They're one of the key foundations of machine learning right now, and which is critical to AI. They're necessary for implementing Industry 4.0 and predictive analytics. I think data quality is fundamental to machine learning and AI. Total quality data management, TQDM, is very, very important. The BART results, very, very promising in economics and in business applications. On this theme of common independent variables are useful for induction and ensemble. This ensemble approach where you have a suite of algorithms making the prediction, I think that only reduces generalized errors and produces prediction in validation, as well as this recurring theme. So what variables are going through the suite, rising to the top through the suite of algorithms. I have a lot of references. I could have put 10 pages of references here, but I list a few. And my area of work in data science back at the University of Tennessee really focused a lot on the green business and the bioeconomy at this point, and how we can use data science to get that to the next level. And it all starts, like I said in my earlier slides, with data fusion and data quality. So I do a lot of work here in automated data fusion and quality. And then I also do work in machine learning and AI, okay, which was really the theme of my talk, mostly focused on random forests. And right now I'm very interested in this BART algorithm. And then I do a lot of industry training in these algorithms and work here, as well as support a number of graduate students in my work. So this is for the students. Don't be afraid to fail. Learn from your failures. Look at this example someone gave me. I didn't know until I got this slide a couple of years ago. You know, Michael Jordan was cut from his high school basketball team. And look what he went on to be, the best basketball player in America, okay? Albert Einstein, teacher said he can't talk. He's 4, he can't talk. He's not going to amount to anything. Well, nothing more said there. Steve Jobs was fired as the CEO of Apple at 30 years old. He was devastated. Came back to rebuild it into a global leader. I think they're a very large company right now, maybe 1 trillion in assets. Walt Disney, fired from a paper, no imagination. Oprah Winfrey, not made for television. She became famous there. The Beatles were cut from their first recording session, etc. Don't never be afraid to fail. Okay, learn from your failures. Don't be disheartened. Okay, and move forward. The key is to be able to detect the signal from the noise. That's why we use machine learning. The great engineer Taguchi, who worked for Toyota, Sony, Honda. The key, he said, is always be able to detect the signal from the noise. And with that, I will entertain questions. And thank you very much.